Excellent. I think it's excellent now.
Can you see it?
Yes, clearly.
Okay. So I'm gonna start it.
Yes, please.
My subject is the effect of nanocellulose on the unconfined compressive strain of MICP-treated kaolin soil. There are lots of methods for ground improvement, mechanical improvement such as dynamic compression, preloading, deep soil mixing, jet grouting, which is a mixture of soil and cement, stabilization by mixing, like chemical stabilization using lime, cement, etc. Using nanomaterials and using the biological stabilization. In this study, I'm gonna talk about these two methods more specifically. To be more precise, nanoparticles have high specific surface area and that may not chemically react with clay constituents. So their effect is limited to changing the texture and compressivity properties of the host soil. Nanomaterials such as nanosilica can act as an active pozzolan. So this pozzolanic reaction can be flourished when they are used along with lime and cement, but this use of lime and cement may create some detrimental environment problem. So there is a new nature-friendly biological method named microbially induced calcium precipitation, shall gradually replace with nature-harming traditional methods. One of these processes that is common in nature is called MICP. This technique relies on a set of biological and biochemical reaction using enzymatic.
I'm interrupting you again, Sarah. We can't see the change of your slides. So we are on your first title page.
I think there's some problem with the internet connection. I don't know why.
Yeah. Maybe try sharing your screen again or showing us a couple of important documents that we need to see if the slides are not changing. Yeah, I can see the nanomaterials now.
I'm here. Can you see this slide?
Yes, I can see your nanomaterials slide.
Okay. During MICP process, what's happening is that urea is hydrolyzed to 1 mole of ammonia and carbonic acid, which spontaneously hydrolyzes to another mole of ammonia and carbonic acid. Then these two products are equilibrated in water to form hydroxide ions and ammonia. The hydroxide ion can increase the pH of the environment that can shift bicarbonate balance to carbonate balance. And this shift can then produce calcium, and ammonia as well can increase the local pH that can lead to produce the precipitation of calcium carbonate. The main idea of the current research.
Sorry for interrupting, but I know the solution now. If you press on edit on the very top, so you can see that yellow ribbon, if you click on edit and then press F5, then your presentation will be full screen. And then as you click, we can see the slides changing. So probably you need to click on an edit button at the very top, the yellow ribbon.
Sorry.
So on the top, you have got the yellow ribbon, edit or make it editable, something like that. My eyesight is really bad. So if you click on that and then press F5, you can change it to full screen, and then you can see the slides actually changing.
You cannot see the change of my slide?
No, because it's not full screen. Now you changed it, so now I can see that, but I don't know what you did.
You can see now?
Yes, whatever you did worked this time, yes.
So you couldn't see anything before?
No, but now I can see the diagram.
Oh.
So whatever you did, keep doing.
So what should I do then? Shall I see?
Whatever you did now, we change the slide, that's good. Keep going, keep doing that. Or You can press that edit button, press F5, make it full screen, and you can follow as you move forward.
Is it okay now?
It is okay now. I can see the diagram. Yes.
Okay. So I was saying the main idea of my current research is to using the MICP process along with nanomaterials in order to enhance the efficiency of this process. Most of the early studies have focused on optimizing components and environmental conditions to optimizing for improving the efficiency of MICP. However, the idea of enhancing biocalcification process by nature-based nanoadditives has not been studied yet. Such an approach can create a better environment to enhance microbial calcification by surging the concentration of calcium, creating more cleation site, and even using MICP products by adding elements that can form new crystal. So this research aims to investigate the efficiency of nature-based nanotechnology on MICP process in kaolin clay as a novel, eco-friendly, and sustainable ground improvement technique. In order to
Sorry for interrupting again. If you look into the chat box, I think my colleagues have put some tips for you how to make it right.
Okay, let me see.
Look into the chat box.
So I did. You cannot see.
Okay. No. So on this, in this case, I would like you to show us those key slides that you think that can deliver the message best, and in favor of time, give us those take-home messages that we need to learn from you.
Okay. So I'm gonna talk about my last.
I think that's a good move, and then we can all see that slide. I can see that you're moving your mouse now. Yeah.
Okay. So
now you see, I can now see the slides changing. This is very good. Please carry on.
Can you see now this slide?
Yes, I can clearly. Thanks.
Okay. Some samples were prepared and a series of unconfined compressive stress tests were done on them. Some of them were untreated, some of them were treated by a mixture of bacterial and cementation solutions, and some of them were treated by this mixture along with nano-silice. So this figure illustrates the stress strain curves of the untreated kaolin. As you can see that the strength and stiffness values decrease as the degree of saturation increase from 50 to 100%. Can you see then this slide now?
Yes, I can see your diagram, actual strain, actual stress, that's your stress strain diagram.
Okay, this slide shows that the effect of MICP methods only on samples after 1 week curing time with different percentage of bacterial and cementation solution. As you can see that the best performance belongs to the sample which was modified by 25% MICP method. And in this figure, you can see that this method was combined with with nanosilica, and after 1 week curing time and with a percentage of 1.5, you can see that the best performance belongs to the sample which was modified by 30% MICP method and 1.5% of nanosilica. So this is 3 times more than the samples modified by MICP methods only, and 12 times more than the samples which was unmodified. And with different percentage of 1 and 1.5 and 2% of nanosilica, you can see that the best performance belongs to the samples which was modified with 30% of MICP method and 1.5% of nanosilica after 1 week curing time. So as a conclusion, the samples treated only by the MICP method, the optimum percentage of bacteria and cementation solution added to the host soil is found to be 25%. Increasing the percentage of bacteria and cementation solution to 30% leads to a lesser stirring and higher saturation degree. And for the MICP-treated samples with 30% bacteria and cementation solution, adding 1.5% nanosilica has created higher stirring in comparison to samples treated by 1 and 2% nanosilica. Thank you very much for your patience and attention.
Thank you very much, Sara. Do we have... Now, since Sara is online, do you have any question from Sara to ask now? No. So thank you very much, Sara. It was quite interesting.
You're welcome.